In this video, we'll look through the lecture notes for section 1.1 on PDE models. A PDE model, where PDE stands for partial differential equation, is one in which the dependent variable is a function of more than one independent variable. So we'll very often use the letters x and t, x standing for a spatial variable and t standing for a time variable. We call u the state or the state variable. As I said, in our examples, usually we'll have x as a spatial variable. There might be a y and a z, depending on how many dimensions we need. And t is our time variable. Some important partial differential equations are the wave equation, Laplace's equation, and the heat equation. These are equations that we will look at in greater detail in the coming lectures. It's a common convention to suppress the dependent variables, in this case x and t. So we write, for example, the wave equation as the second partial of u with respect to t minus c squared times the second partial of u with respect to x. We suppress the utt, we suppress the at x comma t. This is the thing that we suppress. We write the state variable, and we write the variables indicating the derivatives as subscripts, but we refrain from actually including the argument xt. This is just a convention to make it a little easier to write everything down, takes up a little bit less space, sometimes it's easier to follow. On the other hand, sometimes we'll need those variables and then we'll write them out explicitly. Let's start by looking at an example. In this case, we're going to look at heat flow. So suppose that we have a thin cylindrical metal rod of some fixed length, capital L. And just for the sake of argument, let's suppose that it has unit cross-sectional area. So we see a picture here. When we say that it has unit cross-sectional area, that means for any x that we might pick, if you look at the cross-section at x, the area of that cross-section will be unit length or unit area. So that means that it's 1. The area is 1. That's what we're assuming here. So we have here a rod of length L. So we have an x-axis, and we set one end of the rod at 0 and the other end at L, as you can see here. We're going to imagine some conditions that we're going to impose here. For one, we're going to imagine that the temperature at the ends, at 0 and at L, we're going to imagine that the temperature there is held constant at 0 for all time. We're also going to further assume that this rod is insulated laterally, so that means that no heat can escape outside through the sides. The only way that heat can escape is either moving to the right or to the left. So one thing that we should do is we should actually declare our state variable. We're going to call it u, and it's going to be the temperature of the cross-section. So we have two variables, an x and a t. The x tells you where you're at spatially. We're looking at some number x, which represents the distance between the two endpoints in some sense. In this case, x is the distance to the right of the left endpoint. T tells us what time it is. So t is going to be greater than or equal to 0. The initial time is t equals 0. So as I mentioned, we assume that the ends are held at a constant temperature of 0, and we assume the rod is laterally insulated, so heat can only flow in the x direction, either the positive direction or the negative direction. We assume there is a function phi at x that gives the initial temperature along the rod. So at time t equals 0, u at x at 0 at that time is given by this function. So the idea is that this phi of x, this is a given function. So it's known. The idea is that you can measure the temperature all along the rod at time 0. So this is given to us. The equation governing the evolution of the temperature U is what we call the heat equation. Here. The equation says that U sub t, the partial derivative of U with respect to the time variable, is proportional to U sub xx, that is the second derivative of U with respect to x. There's a constant here, k, which is called the diffusivity, and it depends on the properties of the metal and the rod and so forth. We will derive the equation in section 1.3 based on the law of energy conservation and Fourier's heat conduction law. As some terminology, let's introduce some terminology here. Our first assumption was that the ends were held a constant temperature of 0. So we can write that out in terms of the state variable. U at 0, comma t is equal to 0 for all t. So this means no matter what the time is, the temperature at the left endpoint is 0. It's held constant. We have the same for x equals L, so U at L comma t is equal to 0 for all t. These are known as boundary conditions because they're telling us the conditions imposed on the boundary, hence the name boundary conditions. We also have an initial condition. The initial condition in this case is the statement that for all x, at time 0, we can identify the temperature at point x. So U at x comma 0 is phi of x. This is the initial temperature. In this case, we mean initial in the sense that t equals 0. This is the starting temperature. All along the rod, we know what it is. It's given by phi of x. So we have a partial differential equation and boundary conditions and initial conditions, and if you put all of those together, you get what's usually known as an initial boundary value problem. The boundary value problem refers to the fact that we have boundary conditions, and the initial part refers to the fact that we have an initial condition. Here we have both of them, so it's an initial boundary value problem. When the state variable depends on space and time, we say the model is an evolution model. If it depends only on spatial variables, it's called a steady state or equilibrium model. Let's look at an example. This is often known as the Dirichlet problem. If omega is a bounded region in R2, and here I've drawn some randomly selected bounded region. It doesn't have to be a square. That was just convenient to draw. So if omega is a bounded region in R2, and if on the boundary, so this symbol means the boundary of omega. So in that case, the boundary of omega is the actual square, whereas omega is the interior of that square. So we have this bounded region, and the boundary is given here. So on the boundary, there is a given time-independent temperature. So that means if you're measuring the temperature on the boundary, it's always going to be the same value regardless of time. That doesn't mean that the temperature along the boundary is the same everywhere. It just means that it doesn't change over time. But it does depend on x and y. So the temperature at this boundary point might be different than the temperature at this other boundary point. But the point is that at any given boundary point, the temperature remains the same as time passes. So if we assume that this is the case, then the steady state temperature U for any xy in the interior satisfies Laplace's equation. The second partial derivative of u with respect to x plus the second partial derivative of u with respect to y is equal to 0 for all xy in the region. This is for the steady state temperature. The idea is that if eventually the temperature reaches some kind of equilibrium or a steady state, then the function that gives you the temperature in that region, the steady state temperature, will satisfy Laplace's equation. This is an equation that we'll also talk about in greater detail later. What we have here is we have a boundary value problem. We have that u sub xx plus u sub yy equals 0. That's our partial differential equation. But we also have these boundary conditions. We know what the temperature is along the boundary. So this gives us what we call a boundary value problem. It's not an initial boundary value problem because there is no initial condition given for us, because the temperature of the steady state temperature doesn't depend on time. It's the same regardless of time. So there's no initial condition given to us. It's just a statement about spatial variables. So that's all we need. We don't need an initial condition. Let's introduce a little bit more terminology, which you probably know from your ordinary differential equations class. So these partial differential equations that we've looked at so far. So first we had the heat equation here, and the second one is Laplace's equation. In fact, there should be a possessive there. So these two equations are second order partial differential equations. They're second order because the highest derivative has order 2 in each case. The order of a partial differential equation is the same as the order of the highest derivative in the differential equation. These are also examples of what we call linear homogeneous partial differential equations. Let's explain what we mean by all of that. We can write a second order partial differential equation in this form that you see here. This is an equation. We can imagine putting everything on the left side so that there's just a 0 on the right. Then everything on the left will be a function of the spatial variable, the time variable, and also the state variable, but there's also derivatives that are involved. There's the partial derivative u with respect to x or t, and you can also have the second derivatives. So you have on the left a function of all of these things, x, t, u, and all of its derivatives. This is a second order partial differential equation. So that means we don't move beyond the second order. There are no third derivatives here. We say the partial differential equation is linear if this function g is linear in u and its derivatives. Notice we're just talking about u and its derivatives here. We're not talking about the x and t, just the u and its derivatives. What that means is when we say that g is linear in u and its derivatives, it means that they appear alone. So you don't multiply them by each other. And they're all raised to the first power, so you don't have a u squared. You also don't have a sine of u or an e to the u or a u sub x times u sub t. These terms don't appear. That's what it means to be linear. A linear PDE is called homogeneous if every term contains u or one of its derivatives. We only apply this term homogeneous if we have a linear PDE. If it's not homogeneous, we just call it non-homogeneous. Let's look at some examples here. So these are just randomly written down, essentially. So the first partial differential equation, A, is not linear. It's not linear for two reasons. The first term is a derivative of u that's squared. That makes it nonlinear. So that alone would make it nonlinear. But also this term right here is also nonlinear. U times a derivative of u, or a second derivative of u. Any one of these terms would make the partial differential equation nonlinear. In order to be linear, the terms with u have to contain only one term, in the sense it could be u or one of its derivatives, but it has to be that alone by itself. And they all have to be to the first power. So here I have u to the t times u to the t, so I'm squaring it, so it's not alone. And here I'm multiplying these two terms together, so they're not alone. So this is nonlinear. It's also true that b, example b, is nonlinear. The first term, u sub xy, that is a derivative of u, a second derivative of u, which is alone, so that term's fine. The issue comes about here, sine of u. In order to be linear, it can't be inside the argument of a sine or a cosine or any of the other transcendental functions, or indeed any other nonlinear function. It has to just be by itself. So we don't talk about homogeneous or non-homogeneous for nonlinear. The last two, C and D, these are linear. They're linear because they're linear in terms of u and its derivatives. Notice, let's look at C. We have u plus the first derivative u with respect to x plus the second derivative u with respect to t. These are all by themselves, and they're to the first power. There's also this very, let's say, eccentric looking term, sine of xt cubed. This sort of thing is not linear in terms of x or t, but that's okay. When we talk about a linear partial differential equation, we're talking about linear in terms of u and its derivatives. So the fact that we have this sine of xt cubed here is nothing to worry about. So this is still a linear term. It's also non-homogeneous. It's non-homogeneous precisely because of that term. Remember, a linear PDE is called homogeneous if every term contains u or one of its derivatives. Here I have a term which does not contain u or one of its derivatives, so this is non-homogeneous. Example D is homogeneous because every term here has u or one of its derivatives. So it is homogeneous. Well, of course, we have to make sure that it's linear, but it is. It's linear in terms of u and its derivatives. Notice that the coefficients here are kind of exotic in the sense that here we have an e to the xt, here we have a tangent x. So these terms are not linear in terms of x or t, but that's okay because in order to be a linear partial differential equation, we just need to be linear in terms of u and its derivatives. So however wild this e to the xt gets, or tangent of x, or whatever function you might put there, as long as it's just a function of x and or t, then it's fine. It doesn't affect the linearity of the partial differential equation. What's important is that the u is by itself in terms of there are no other u terms. There are no derivatives of u multiplied by it. It's just u to the 1. And this is u sub t to the 1. And this is the second derivative of u to the 1. So you're not multiplying the derivatives together. You're not squaring them. You're not evaluating them using some transcendental function, such as sine or cosine or tangent. There is a tangent here, and there is an exponential there, but they don't have u's inside their argument, so they don't affect the linearity of the partial differential equation, because the partial differential equation is linear if g is linear in terms of u and its derivatives. So whatever kinds of crazy functions you might see in terms of x's and t's, those don't affect the linearity of the partial differential equation. It's common to introduce what we call operator notation. The idea is that you define an operator which evaluates based on some sort of function that you put into it. And it's a differential operator because you take this function u and you evaluate L at u and you get something involving derivatives. So let's look at this first example, example A up here. So we define L of u to be equal to the term on the left. So ut quantity squared, u sub t quantity squared plus u times u sub xx. So the way this linear operator works is you give it a u and the output is the first derivative of u with respect to t squared plus u times the second derivative of u with respect to x. The differential equation is then the statement that L evaluated at u is equal to 0. This operator notation is very handy because it makes certain differential equations much easier to write, as you can see. Our second example, well, we don't look at the second example. Let's just skip to C. L of u is equal to u plus ux plus utt. So that is u plus the first derivative of u with respect to x plus the second derivative of u with respect to t. So the way this operator works is you give it a u, and then it computes u plus u sub x plus u sub tt. Then our differential equation here in C is the same as saying that L applied to u is the opposite of sine xt cubed. What we've done is we've taken this sine xt cubed and we've just moved it to the other side. And that gives us our differential equation. our fourth differential equation, it's the same idea. L evaluated at u gives us the left side, ext times u plus ut plus tangent x u sub tt. And the differential equation in D is simply the statement, again, that L of u is equal to 0. Now, the L in A is not the same as the L in D, of course, or as the L in C. We call L a differential operator, and we call it linear if it satisfies these properties here. L at u plus v is L at u plus L of v, and L at c times u is equal to c times L of u, where in this case, c is constant. This c is a constant, so in other words, you can take the constants out. If L satisfies these two properties, then it's called a linear operator. So the first one is not a linear operator, and that's why the differential equation is nonlinear. C and D, these are both linear operators, and that's why these are linear differential equations. If L is a linear operator, then L of u equals 0 is a homogeneous equation. And it's non-homogeneous if L of u is equal to some function f, where f is non-zero. So you can see in our examples, remember we only talk about homogeneous and non-homogeneous if L is a linear operator. So the two linear operators that we had were from C and D. So C is non-homogeneous because we have L of u is equal to some function. Here we have f of x comma t is equal to minus sine xt cubed, which is certainly not the zero function. So this one is non-homogeneous because we have L of u, where L is our linear operator. We have L of u is equal to some non-zero function. On the other hand, in D, L of u is equal to 0, so that's linear. Or homogeneous, I mean, that's homogeneous. Now, you might wonder, in C, so for C, can we define L so that L of u is equal to u plus u sub x plus u sub tt plus sine xt cubed, like so. Now, if you do this, well, you can certainly define it like this. However, there is a problem with it. It is true that now we have L of u is equal to 0, but the problem is that this L is no longer linear. Because if you look at an L of u plus v, then you're not going to end up with L of u plus L of v, because you're going to end up with that term twice. So this is not going to be a linear operator anymore. So you can't talk about it being homogeneous or non-homogeneous. So that's why we don't do it that way. So that's why we let L of u be equal to u plus ux plus utt. This is linear. It means our differential equation is non-homogeneous, but that's okay.